The last years, the machine learning has taken hold of almost all AI talk. But what if I told you there is a type of AI that has been researched by even the ancient Greek, Indian, and Chinese thinkers? It is the field of formal logic and reasoning. In modern AI development, logic still plays an ever-growing role as we try to instill formal reasoning into our models. Today we will discuss the concept of SAT solvers and propositional logic to understand how computers are able to compute truths in formulas. So let's get started with propositional logic. Propositional logic is a language to express reasoning mathematically. Imagine you have an assignment due. You can take from this 3 truths. If I do not finish my assignment, then I will be stressed tomorrow. If I watch Netflix tonight, then I will not finish my assignment. I do not want to be stressed tomorrow. Now this we can actually heavily simplify. Just try to simplify this with normal language. If not assignment, then stressed. If Netflix, then not assignment. Not stressed. These are the things that you want to have true. This is like kind of you can think of as a way to express yourself mathematically with this. And if you do so, you might sound like Kevin from The Office. Then after that, we can add the syntax to make it proper formal logic. The right angle that you see here in red is supposed to be a negation, meaning not. So not assignment. And then the arrow is supposed to read like if then. So if not assignment, then stressed. If Netflix, then not assignment. And then lastly, we just have not stressed, like you don't want to be stressed. And of course, we can shorten the variables too, to make it sound just if not A, then S. If Netflix, then not A. Lastly, not S. Now let's actually assign some values to this. Let's say I will do my assignment, but I won't watch Netflix and I will not want to be stressed. Then from this, we can assign A to be true, N to be like Netflix to be false, and stress to be false. This is what we prefer for our outcome. We can put this into the formula, and not true is just false, and then not false is true. So we just do that. So we have if false, then false, and that is true. Like if you don't do anything, then you will not get any result, right? And then true is just true. So we get that all these will be true if we do the assignment and do not watch Netflix. So this is good. But what if we decide to do our assignment and watch Netflix, but we do not want to be stressed? This gives us A true, N true, and S to be false. If we plug this into our formulas, we will get true, false, true, meaning this can never be all of it true together. This is called satisfiability, and a set of formulas is satisfiable if there is some assignment that makes all of them true. A set of formulas is unsatisfiable if no assignment makes all of them true. And a formula is valid if it is true in every single possible assignment. This was a simple example, but propositional logic is actually very powerful. You can find it in hardware, software verification, in cryptography and security, and something that is very important for us in machine learning, to do rule learning with it, meaning we can actually try to understand and get these rules, like this logic, from specific data itself. Therefore, with this, we can actually have a more explainable model. But how do computers compute propositional logic? The answer is with SAT. Now, SAT itself is basically like, you can think of like a technique or a set of techniques which computers can actually then use to check for satisfiability on a formula. SAT checks if a formula is satisfiable based on a bunch of true or false values. Let's try it out online. So I'm here on Limboole, which is from the JKU, like a university SAT online checker. So if I do A and B, then I will get that A and B have to be true so that the formula is true. However, if we put in our formula from before, where we say not assignment, it equals to, so if we do not do our assignment, we will get stressed. And if we watch Netflix, then we will not do our assignment. And lastly, we do not want to be stressed, so not stressed. If we then click on run, we get here that assignment must be true. So 1 equals true. Then stressed must be false and Netflix must be false for us to basically have this formula true. Okay? This means we can only be not stressed if we actually do our assignment and we skip Netflix for tonight. So now we will actually go into learning how these SAT solvers actually work efficiently, because they can actually blow up with the complexity. Now we just put in a simple example, but they are known to really blow up with complexity. So we will be covering these 7 techniques to make it efficient. First of all, CNF. This is a type of normal form where you basically take here our formula that we have before, and instead of ifs and all of that, we just basically make this into and or statements. Meaning we transform our if statements into or statements. And there are some other techniques. There's like a list of things that you can do, where one of them equates into the other. I will not be covering this, but you can look it up online, inshallah. If we try to solve this now, we see that actually the S here must be false. So if I have here not stressed, then for this entire formula to be true, we actually need to have S false, because not false is true, right? So if this is then false, we can also put it here in the A or S. And then A must be true, because in a or clause, basically one of them must be true, at least. So since S is already false, A must also be true. And then we set true to all the A values. And now N must be false, because we have here the not true for the A, meaning this is false. And so we need another false here to make this then true, because not false is then true. And this gives us then true, true, and true. And this, of course, is true at the end. So this is basically an overview of what the computer does with these normal form formats to actually get to a solution. Now, since these formulas often blow up with complexity, there is a technique which helps you basically keep this in check. And what you do here is basically you assign all of these clauses a new variable. So instead of doing all of this, you just have C1, C2, and C3. Now, this does not equate the original formula. However, if you do this, you can actually check for satisfiability. So it's not the same formula, but it still has the same satisfiability. Next is resolution, where if we look in resolution, we see here an A and a not A. And here's the thing. If both clauses are true, then no matter what A is, you must have either S or not N true, So A, basically, you can think of it as it doesn't then matter, Since you have A in one clause and not A in the other, it doesn't matter if it's true or false. What does matter is the S and not N. So we can just combine it like this then instead. S or not N, one of them must be true for the clause to be true, and not S. And this is the resolution method. Next, we have blocked clauses. And for this, I want you to imagine the and not s is gone. Just like this. This clause blocks the formula and is usually deleted. The thing is, if we have only s or not n, we can never tell what is false and what is true with that, So SAT solvers usually just delete them since they're not useful. And this does not change satisfiability if we delete this clause. Next is BCP. Now in BCP, it's basically what we did before with trying to isolate one of the elements like the S and then just basically removing it as we just did before. So not S must be true to make the formula satisfiable. Next is DPLL. So if we have here S or not N, like we had before, and we do not know what to do, basically what happens is we pick a random literal and then we set it to true and just try to play it out, see what would happen. And if that fails, we then just set it to false instead and just play it out and see what happens. And then we continue to the next variable. Lastly, we have CDCL, which builds upon DPLL, but the problem with DPLL is it might waste a lot of time pursuing dead ends. So what CDCL does is it optimizes this by looking for combinations that can never go together. For instance, if we have here S is false and N is true, this can never be true at the same time, because this would make this clause in front of us always false, which we do not want. Therefore, CDCL would never pursue it. So it basically has, you can think of like a bit like a list of things that would never work, so they would never pursue it. It's just an optimization of DPLL. Lastly, I want to quickly go over how we can solve Sudoku using propositional logic and SAT solvers. I think this is very nice to show, since I guess we do have then an AI with propositional logic, which beats Sudoku every time. So imagine we have here this Sudoku grid. For simplicity, we will just do 2x2 grids. So we have here 4 numbers on the grid. So the first thing that needs to be true is that for every single cell, at least one object needs to be here, meaning 1, 2, 3, or 4 must be in every single cell. But this could only mean, but they can of course not all be true at the same time. If one number is true, that the others are not true too. And that's what we do here on the right. Next, we also have to check the entire column to see that in a column, it only has one value per column, so it needs to be 1, 2, 3, 4 per column. So we check that. And then the same thing with the rows. And then also for the boxes. And then the final formula is the cell constraints plus the row constraints plus the column constraints plus the box constraints. And then lastly, the given numbers that we got. So the 1, 2, 3, and 4 that you see on the screen. For that, we can write a quick Python program where we have here the variable name and just like a list of clauses. And then here we first add all of the cell constraints. Then we add all of the row constraints and the column constraints. Then we add here the box constraints. And then lastly, we just add them all together. And then we copy paste it into Limboole again. And we get our final solution. Thank you very much.